You get my message on this.
Uh, I don't, or remind me what we.
It was just me saying I wasn't making it talk, so I was last week.
Oh, yeah, no,
Optimization.
yeah, no problem.
Okay.
I read it and I registered, I'm like, okay. That's
As long
fine.
as
And
I just didn't want it, I just didn't want you to be sitting in an office. Like, where is this guy?
Oh,
He
no,
doesn't
no,
Be here.
Yeah, no problem. I mean, even then, I used to, because you guys are so busy, so.
Yeah, I'm gonna try to make it on this upcoming Thursday, because I also want to talk about that project.
Okay, yeah,
Project I'm super nervous about.
yeah, no, for sure. Yeah, let's talk this Thursday.
Okay,
Mhm.
it is it's individual project, right? That's what you're
Yes.
saying?
Yeah.
Have you ever had anyone come to you to help them with a fluids project? So you've probably done the fluids project where they're optimizing the flow rate and the efficiency within a pump?
The pipes.
Yeah,
I've seen it. I mean, I haven't done it front to back, but I've just answered just pointed questions here and there.
okay. You'll probably get some from me.
Okay. Dr. Mayroff.
Yeah.
Okay.
Yeah.
I'm familiar with it. I've never done it, never seen the whole, just answered.
I can show you the problem statement so you have more context for when
Sure.
students come to you.
Yeah.
I don't have it yet. We're getting it on Thursday, I think, so.
Okay. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Great.
Good, hanging in there. We're almost at Thanksgiving. We have 2 more full weeks to go, so this week and next week. Then we have a week off. So I apologize a little bit today. I am feeling a little bit sick. I took my little cousins to an anime convention over the weekend. One of them is 10 years old, the other is 16. And kids are kind of gross, and so I bought lunch for us, and then my 10-year-old cousin's like like all over the food. I was like, well, I've already paid $25 for this bowl of noodles. Like, I can either pay another $25 or I could risk getting sick. So I risked it, and I got sick, and so I'm kind of dealing with the consequences of my actions, or consequences of my cousin's actions. So I might sound a little bit nasally, and I might be a little bit out of it, but because I'm all drugged up on Dayquil right now, but hopefully it's not going to affect me too much. Okay, so the plan for today is we are going to continue on with our lecture notes. So we left off last Tuesday talking about pattern search. So I did want to finish that up today. I wanted to kind of show you the code for that as well. It's very similar to coordinate search, except there's just kind of one little extra step that we'll kind of just we started talking about last time. Okay. All right, so we'll do that. We'll look at the code, and then we'll start looking into Nelder-Mead optimization as well. So Nelder-Mead, that's going to be the last optimization algorithm that we'll go over in this unit before we start talking about constraints. Nelder-Mead is really interesting, and it's probably the most modern, versatile algorithm that's out there. So it's kind of really important that we go over that as well. All right, so other announcements. Hopefully everyone got my email today about the midterm exam next Thursday. So that is November 21st here in class, right? So the format of the exam will be the same as the last exam, although I promised the last exam I'll make this one shorter, and I will do that. So this exam will be shorter than the last one. But besides that, everything that you can do for the first exam you can do here. Writing utensil, calculator, cheat sheet, front and back, 8.5 by 11. Same rules as the last time. Okay. I posted the study guide today, so make sure you take a look at the study guide. And in terms of content, there's only be 2 homeworks worth of content on the exam. So it's going to be homework 4 and homework 5. Okay. Right. So one thing I noticed about homework 4 is that most people kind of just implemented the MATLAB code for it. So for most of you guys did a good job with that. But just know that on the exam for the 1D optimization algorithms like Newton-Raphson, interpolation methods, exhaustive search. You should know how to do those by hand as well, or at least the first couple sets, right? For the multidimensional algorithms, those ones I'm going to ask you to do pseudocode. But for the 1D optimization, you should know how to at least do some of those calculations by hand. Okay. So likely what I'm going to give you on the exam, there's going to be 2 problems. One of them is going to be a 1D optimization problem. For that one, I will give you an objective function, and I'll say, use such and such method. So, let's say use Newton-Raphson method, or let's use a dichotomous search, and show me the first 3 steps of the algorithm in terms of how it would go. Okay, so you should be prepared for that. And then for the multi-variable optimization, probably something similar. I'll give you an objective function. I'll give you an objective function. But instead of carrying out the algorithm, you should at least be able to tell me how it works. Or maybe I give you some random numbers. So maybe I say, let's say the first 3 random numbers that MATLAB will generate are these ones. And so show me what the first step in the algorithm would look like if you were to do a Monte Carlo, if you were to do a random walk. Question.
For like the first X steps, would that be like iterations, you mean?
Exactly.
Oh.
Yeah. So for example, let's say I asked you to do a problem with dichotomous search, and so I should, you should be able to show me that if you did 3 steps, the domain is going to get halved, and then halved again, and then halved one more time. So you end up with just 1/8 of the domain left over. Okay? And you should show me kind of the whole steps that you took to get to that. All right. Any questions on this topic, or just on the exam, or just anything that we've covered so far? Okay, all right, so let's go ahead and pick up where we left off last Tuesday. Okay, so last Thursday, excuse me, last Thursday we were talking about the pattern search. Okay, So we introduced the idea of pattern search as being basically like an improvement over coordinate search. Okay. Because if you remember our coordinate search algorithm, basically the idea with coordinate search is that you're optimizing basically one variable at a time. Okay. So in each step of coordinate search, you're holding all of the other design variables constant, and you're just focusing on one. And then you can use you can then use a 1D method to optimize just that one variable. Okay. All right. Say coordinate search. Now, the way coordinate search works is that normally you have to repeat this over and over and over again until you reach the optimum. Because oftentimes when you change one variable, it changes the properties of the other variable, and so you kind of have to do kind of a cycle. So let's say if you have an objective function with three variables, okay, you have x1, x2, x3, okay. So the way coordinate search works is that it kind of goes in kind of a round robin type of flow. So on the first iteration, you're going to be optimizing x1. Second iteration, you're going to be optimizing x2 while keeping the other variables constant. And then on the third iteration, you'll be optimizing x3. Then the cycle just repeats. So on the fourth iteration, you're going to be optimizing x1 again, leaving the other two constant. On the fifth iteration, you're going to be optimizing x2, leaving the other two constant. Sixth iteration, and so on and so forth. So this kind of table, and of course, this is going to repeat. Okay. So the idea with pattern search is that after you do a full round robin, so after you've optimized each design variable once, right? Then the idea with pattern search is that a pattern starts to emerge in terms of how you should travel to get to the optimum. And basically the idea is that the pattern that emerges is that if you take each improvement or each change in each variable and you treat them as a vector and you add them up together, that's going to give you what's called a pattern direction. And so this is kind of the illustration that we had last time. So we kind of the only way we can illustrate things is in 2 dimensions, but kind of try to imagine things extrapolate to 3 dimensions, 4 dimensions. Well, 4 dimensions, it's really hard to do. But basically in 2D, let's say that we do one full round. So one full round means that we optimized over x1, we optimized over x2. Okay. And so let's say that after one full round of optimization, we end up at this point right here. Okay. What we can do from here is that if we do a vector addition of the 2 changes that we made, so we do a vector addition of our change in x1, we add that to our change in x2. Okay. And so we end up with a pattern direction that looks like this, okay? What we can do is we can add that pattern direction to our latest point, okay? And that's the idea is that this is gonna get us closer to our optimum, as long as our objective function is fairly smooth. Okay? So if our objective function is smooth, then by traveling along this line, this will get us to our optimum faster than if we just kept doing coordinate switches. Okay. Okay. So the formula for doing pattern search is actually quite simple. And so in order to get this pattern direction, if you think about this from kind of a vector point of view, right? One way for us to get that direction is to just do a vector subtraction of our starting point before the full cycle and our ending point, after the full cycle. So the formula for this is quite simple. So PI vector here, PI vector is going to be this is our pattern direction. You can call it the pattern vector if you want. This is going to be equal to xi minus xi minus n. This xi here, this is our ending point after the full cycle. And this xi minus n, this is our starting point or the starting design point before we initiated the cycle. Okay. And so the only thing that you have to keep track of here is that you have to keep track of your starting point in the cycle. So that implementation wise, that means you're probably going to have to use an additional variable to store that starting point. But once you have that variable, you just do the subtraction between. And the nice thing about MATLAB, I think looking at your homework, I think everyone in the class is going to be using MATLAB. MATLAB does vector subtraction very, very easily. So you just do vector 1 minus vector 2. Okay. Which you would think, that's how it should be in all programming languages, but most programming languages actually make vector addition much more complicated than it should. So MATLAB is kind of nice in this sense. Okay, so after getting the pattern direction, what we have to do is we have to take a step in that direction. And so to take a step, we just use our normal stepping formula. The only thing is that the direction that we're stepping in is in the PI. We have xi plus 1 equal to xi. So xi here has the same interpretation as above. So this is kind of our ending point after we do kind of a full cycle. So we've done a coordinate search in each, or a coordinate step in each design variable. Okay. Plus alpha times pi. Pi is the pattern direction that we defined above, and alpha here is the step length. And then after you take a step in the pattern direction, then you restart the entire cycle. So you go back and you do a coordinate search for each individual variable. After you do that, another full cycle, you get another pattern direction, and then you take another pattern step, and then you just kind of recycle from it. Okay. After stepping in pattern directions, after you take a step in the pattern direction, you're probably not done. So you're probably not at the optimum yet. So you should go back to coordinate search and then kind of start the process all over. Okay. And that's all pattern search is. So pattern search is basically just, for the most part, it's the same as coordinate search. The only thing that's different is that you're adding this additional step to not only determine the pattern direction, but also step in that direction as well. Okay. The nice thing about this kind of addition here, normally whenever you're looking to improve an algorithm, usually it involves additional evaluations of the objective function. Here we don't strictly require any additional evaluations. You just kind of add another step here. Okay. So pattern search is kind of a really nice improvement to an already pretty good algorithm here that doesn't really add that much cost to us. Okay. All right, any questions on the idea of pattern search? Yeah.
So then would you be evaluating the objective function at this like last part here rather than the intermediate?
Yes. Yeah. Yeah. So I guess technically you're adding one additional function evaluation because you're taking a step. But ideally that step is better than if you did another coordinate. Okay, so what I've shown you here, this is kind of the very most basic pattern search. And actually, if you look up pattern search in any kind of textbook, they've kind of added a lot more bells and whistles to kind of make it perform even better. But this is kind of the essence of pattern search, at least at least how it was kind of originated. Okay. Now there is one additional issue with this, and it actually technically was an issue with coordinate search as well, which is how do we determine these step lengths? Okay. So previously, when we did coordinate search, we did kind of something pretty clever last Thursday, if you remember it. So, the idea with coordinate search is that you're basically breaking the problem down into a one-dimensional problem. Okay? What happens when you kind of hold all the design variables constant except for one, you can treat it as if it were kind of a 1D problem. And we kind of took advantage of that fact by, basically doing a classical method where we take the derivative of the objective function with respect to one variable, set it equal to 0, and then we use that to define the step length. Okay. Now that process is not always going to be available to us. Now, another way that we can determine the step length is to apply kind of a 1D optimization algorithm. So we can use like Newton-Raphson, quasi-Newton-Raphson, we can use interpolation methods, dichotomous search, things like that. Oh, question, sorry.
Does pattern search, is it still, I think I understood it right. Is it still doing X1 and X2 individually, or is it now doing X1 and 2 and then using like an equation of a line to connect those points?
That's exactly what you're doing. So
you're doing both at the same time and then connecting them?
Exactly. So you have to do X1 individually, X2 individually. And then you add kind of an extra step there where you kind of move it.
Oh, so instead of working with points, you're working with vectors now.
Exactly, yeah, yeah. So it kind of has I think it's easiest to understand or to interpret using vectors. We'll do an example where it kind of becomes a bit clearer. Right, so for most cases, if you're trying to determine the step length, that's actually the hardest part of coordinate search and pattern search is determining what that step length is. And so before we launch into another example, I did want to go through another method for determining that step length without having to take derivatives. Okay. So whether it be coordinate search or pattern search, determining the right step length is kind of critical to the entire algorithm. So there are lots and lots of really clever ways to determine the step length. In fact, if you go into the textbook, there's kind of a whole, there's like 10 pages on determining this. And there's lots of things you can do, right? And so I just want to kind of illustrate this is kind of just one way that we can do this. When you're not able to take derivatives of the objective function, then you kind of have to do something clever, right? So here's one way that we can do it. The idea with the step length is that we want to take the biggest, ideally we want to take the biggest step possible in the direction that we're given, to improve our objective functions. Okay. So here's what we can do. Okay. So if we start with some kind of initial step length, and this is something that we can kind of predetermine, before the algorithm begins. We'll call that lambda naught, or lambda 0. The good thing about coordinate search and pattern search to a degree too, is that each step of the algorithm, from each iteration, our direction of travel is kind of already predetermined, okay? And so when our direction of travel is already predetermined, the only really kind of consideration that we have to make is, whether we should step in the positive direction or the negative direction. remember, when you have a predetermined direction, then essentially your problem just becomes a 1D problem. And so, 1D problem, basically you should think about whether we should step to the right or to the left. Okay. If you think about it from this way, this is basically the same kind of very similar kind of a mindset that we had with dichotomous. Okay. And so with a predetermined step length and basically a direction that's already determined, you're going to check, you're going to perform basically two function evaluations. One, a function evaluation means, we're going to take a step in the positive direction, and we're going to evaluate the objective function when we take in the negative direction as well. Okay. Positive step. Okay. So positive step, we're going to evaluate the objective function at f of x plus lambda naught s. Okay. And so in that case, we take a step in the positive direction of s. With s vector here, this is our step direction. And the negative step, we're going to take f of x minus lambda naught s vector. This s vector again is our step direction. Okay, so the only difference is that we're taking a positive step, we're adding the lambda times s, or we're taking a negative step, we're doing x minus lambda times s. Okay. So hopefully when we do this, one of these will lead to an improvement of the objective function. And if it does, that's great. And so whichever one leads to an improvement of the objective function, maybe both of them will lead to an improvement of the objective function. And so you're going to choose the direction that leads to the bigger improvement. Okay, so that's kind of the simplest, case. So if that's the case, you can take a step in that direction and then just kind of move on with your bike, or move on with the algorithm. Okay. But what can happen sometimes is that neither of these can lead to an improvement of the objective function. One may make it worse than the other one, but if neither leads to an improvement, then if you think back to our logic of random walk, right? In random walk, when we had a direction, if we took a step, and if it didn't lead to improvement, then that we just don't take that step. Okay. But we have to take a step, right? It's not like random walk where we can just generate another direction. Our direction is already fixed, right? And so we have to take a step. We just our step in this case would be too big. Okay. So if And so if neither of them leads to an improvement, we reduce the step size, very similar to how we did random walks. If you remember from random walk, eventually we reach a point where we have to reduce our step size as we get closer to the optimum. Okay, that's likely what's going to happen here as well. question.
So do we have a different step length for every variable then? And would we only reduce that ones?
Yeah, no, that's a very, very good question. And actually, this was kind of an issue with the project last year too. So last year, so I made your guys' final project a little bit simpler, so this is not gonna be as much of an issue. But if you're running an optimization problem where each of the variables have very different nominal values, right? And so for instance, I'll just tell you what happened with last year's project. So last year's project, you know, I gave them a similar truss structure. But I also had them optimize over the material properties as well. And so one of the material properties being the Young's modulus of the material. And so Young's modulus, if you're aware, for most materials are usually in the megapascals or the gigapascals kind of range. Meanwhile, the lengths are in orders of, maybe 50 to 500, right? And so what happened was that, people were choosing their step lengths based on the lengths. And so they're only changing the Young's modulus by factors of, 25 at a time. And so the Young's modulus just would not change at all. So if you do have an issue where your design variables are very different in terms of their nominal values, you do have to have different stepping. But for your guys' project, you don't have to worry about that. I've eliminated the Young's modulus as a variable, but that is a very good one. And so I was looking at everyone's responses and like, oh, everyone's Young's modulus is exactly the same. I'm like, oh, that's the reason why. It's because yeah, you need a separate variable. But okay. So to reduce the step size, we basically take lambda is equal to r times lambda naught. Okay. For this lambda out here, this is the new step size. Lambda naught here is the old step size. And r is some factor here that's less than 1. Now, what should you set for R? Well, that's up to you in terms of how aggressive you want your algorithm to be. And so if you want to, make your algorithm, not reduce the step size so much, then you can set it to something high, maybe like 0.95, right? So you can kind of take small incremental reductions in the step size. Or if you want to just go really fast, you can set R to be something like 0.5 or even more aggressive, like 0.3 or something like that. Then your step size is going to be reduced very, very quickly. It depends. And it depends on the problem. It depends on kind of how aggressive that you want. Okay, and so the hope here is that after reducing the step size, you're going to again kind of test the waters. And so you're going to take a positive step and a negative step with the new reduced step size. Hopefully at this point, after you've reduced the step size, it will lead to an improvement of the objective function. And so if that's the case, then you just choose that direction, you choose that new step size and just continue on. If not, then you reduce the step size again. All right. So it's a little bit tedious, and you'll see once we get into the implementation details in MATLAB, you'll see that it's a little bit of a tedious process. But at the same time, by doing this, you also get our convergence criteria as well, right? Because one thing we can say is that if you have to keep reducing the step size, and eventually your step size gets so small, so minusculely small, then, we're probably at the optimum already, right? And so what that tells us is that, we can't take any steps from this point and improve the objective function. So that means we must be at the optimum. Okay. Okay. So this method of kind of determining the step size, not only that, but determining positive and negative, it's a little bit of a combination of kind of the logic that we had with dichotomous search and a little bit of the logic that we use in random walk as well. Okay. All right, any questions on this before we jump into an example? Okay, all right, so let's do an example. Well, it's the same example that we have been doing. So I think this is probably the fourth time that we've done this example. But it's good because we know the answer to it. Okay, so let's do a two-dimensional optimization. So let's minimize the following objective function. We have f of x1 comma x2, okay, equal to x1 minus x2 plus 2x1 squared plus 2x1 x2 plus x2 squared. Okay. With coordinate search and pattern search, we need a starting point. So let's start from 0, 0. And with pattern search, we have to define a few more parameters here. Okay. So we basically have our initial step length in the coordinate search steps. We have our step reduction factor, and we have the initial step length in the pattern search step. Okay. Let me go ahead and list those out. Lambda naught. So lambda naught, we're going to say 0.5. This is our starting coordinate step length. R here, R is 0.5. So we're going fairly aggressive here. So R here, this is our step reduction factor. And then we have alpha naught. So, in this implementation, we're taking the coordinate steps and the pattern steps kind of separately. So alpha naught here, this is our starting step length for the pattern search step. All right, so quite a few parameters here, but just because we're using this new method for determining the step length, but hopefully once we look at the code, it's a bit Okay. Remember, the idea with pattern search is that we're first going to do a step in, we're first going to do coordinate steps in each of the design variable directions. Okay. So for this problem, we have two design variables. So we should have two coordinate steps. Okay. We're going to take a coordinate step in the x1 direction, a coordinate step in the x2 direction. And then from there, we're going to take a pattern step, kind of using that kind of vector interpretation, in kind of a slanted x1, x2 direction, depending on what we get from the first two steps. Okay. All right. So I'm going to show you the code for this, but before we look at the code, are there any questions on this example here? How it's set up? Okay. All right. So let's go ahead and jump into the code. So I'm going to share my screen here. Okay. All right, so once again, this code is available to you on Canvas. And so if you look under the files page of our website here, you should see it's UNLP example 4 pattern search. Okay. Okay. So let's go here. All right, so the code here is a little bit longer here, so it's about 106 lines. Not terrible, but also not short anymore. Right? Okay, so the problem that we're optimizing here is given by this objective function, right? And so what we say here is that we also need our starting point. Okay, so we're starting from our point 0, 0. So that means we have a starting point or starting value of 0 for x1, a starting value of 0 for x2. And we're going to evaluate our objective function at that location. So we're going to plug in 0, 0 into this objective function here. And that's our initial objective function value. We're going to need that when we, when we're comparing things for the step. Okay, you can see another thing that we set here is that we have to define the maximum number of iterations, and so at most we're going to take 50 steps or 50 cycles, right? And we're going to define all of our pattern search parameters here. So we have S naught, R, and alpha naught. Question.
What's the convergence threshold again?
Yeah, good question. So, whenever you have an iterative algorithm, you have to have some way of knowing when the algorithm's done. And so this convergence threshold is, once the step length drops below that number, then we know that, we can't make any more improvements. Right?
Okay, I see.
So, there's going to be a part in this algorithm where, we're going to be reducing that step size. If that reduction is so much that it drops below 1e-7, then we say.
Why did you choose 1e-7? Why so small?
Yeah, so you can choose other values too. So this is something that you kind of can play with yourself. If you choose a higher number there, then it's going to converge faster. So if I change this to let's say 1e-2. So that's going to converge faster because it's going to take less time to get to that number there. But it may not be as precise because maybe there might be some additional improvements that you can make there.
So you go so small just for precision's sake?
Exactly. Yeah. I picked 1e-7 just because I know this problem in particular has a very clearly defined solution. So we should be able to get basically right on top of it. But for your final projects and for more difficult problems, you may want to loosen that up a little bit. And so you may want to choose something like 1e-2 or even 1e-1 too. It kind of depends on the problem. Because for your final project, I can tell you with certainty that if you use something that's really tight, like 1e-7, your code's going to be running for a very, very long time because it's going to be really hard to get that close to the optimal. With the problem is that complex. Okay. All right, so from there, we also need to set variables here to save the best values for the parameters. Okay, so x1 best, x2 best, and f best. Okay, so we've only done one function evaluation at this point, and so we're just saving the initial point here. And then from there, we jump into the algorithm itself. Okay. Okay, so the first steps in a pattern search is to do coordinate search, right? So remember, think of pattern search as kind of an improvement over coordinate search, right? So in this first section of the code here, okay, we're going to be making changes to just one of the variables, okay? And so in this case, we're making changes to x1. Now, the big difference in this code compared to the one we went over last Thursday is that we're using this new method to determine the step length as opposed to, taking the derivatives, which is what we did last time, okay? So now that does make our code quite a bit more lengthy. And in fact, we have to have this kind of while loop inside our for loop. Okay? But the positive thing about this is that we're not relying on objective function derivatives. Okay, so the main thing here is that we have to check a positive step and we have to check a negative step. Okay? And so by checking a positive step, we're adding s. So s is our step length here. We're adding that to x1. Okay? And so we're valuing the objective function at that location. And we're taking x1 down where we're subtracting that step length and then evaluating the objective function. Okay. Now, hopefully, after we check up and after we check down, one of these will lead to an improvement of the objective function. Okay. And so that's what we're checking here. Okay. So you can see we have a while loop here, but one way that you can interpret the while loop is as an if statement. Question? Yes.
Never mind.
Okay. So the only way we enter this while loop here is that if both F1 up and F1 down, if neither of those lead to an improvement over the objective function. So we say if F1 up is greater than FB, FB is the objective function at our current location. If F1 up is greater than that, and if F1 down is greater than that, okay, we have an additional check here on the convergence. Okay, so as long as our step length here is greater than our convergence threshold, and so if we check up, we check down, we don't have any improvement, then we reduce the step size here. So this line here reduces the step. Okay. All right, so after we reduce the step length, you can see during this section here is identical to what we have up here. So after we reduce the step length, we basically reevaluate the objective function in the positive direction and the negative direction. Objective function. And remember, this is with the reduced step length. And then here we are reevaluating the objective function in the negative direction. Okay. And then we go back up to the conditional for them. Okay. And so once again, we're going to check if F1 up does not lead to an improvement, and if F1 down does not lead to an improvement, then we reduce the step size again. Okay. So we have kind of a while loop here that kind of implements this reduction in step size and step here. Okay. And so once we reach the end of this while loop, kind of one or two things can happen. One thing that may happen is that we have, we've seen an improvement. So either if we step in the positive or negative direction, that leads us to improvement. Okay. And so if we found an improvement, then we take a step in that direction. Okay. And so you can see here that we're choosing whether we're going up or down. So if F1 is less than F1 up is less than F1 down. Okay, that means we see an improvement by taking a step in the positive direction. Else we take a step in the negative direction. Okay. And then we print out our step. If we reach the convergence threshold, so if this condition was met, then remember we set our convergence threshold to be extremely small. So we're going to be forced to take a step, but it's going to be a very, very kind of small step. Okay. And then just for debugging purposes, I printed out the step length here just so that we can kind of see the evolution of that step. Okay, so from here on out, we're going to repeat the exact same thing for the second direction. Okay, so everything that I've highlighted here is just a repeat of the section that we just went over, but we're doing it for the x2 direction. Okay. And then from here on out, we're going to do the exact same thing, but in the pattern direction. Okay. So remember, the pattern direction is that you basically take the difference between where you stepped in the x1 direction and the x2 direction. You do a vector subtraction there, and that gives you your pattern direction. Okay. And so we can take, you can see here, we're taking that step here. And once again, we're doing the same algorithm here, we're checking that checking that direction.
What was that second copy and paste for? What direction was that in?
So the second copy and paste, this, you mean this section here?
Yeah, from the first, yeah, that one.
So this is for the X2 direction. So there's kind of three sections of this code here. So remember this objective function, we have two design variables. And so first we're going to take a step in the X1 direction. Then we take a step in the X2 direction. So that's classic coordinate search there. And then after that, we take a step in our pattern direction. So that's kind of the third step of this process. All right, and so after that, we save the pattern step. Okay, we check if we've converged, and if we converge, then we break out. If not, then we come back up, and then we repeat kind of this whole process. Okay. All right, so let me go ahead and run the code just so you can kind of see it working in action. We can kind of see the end. Okay. All right, and so what you can see from here is that our best value for X1 is -1. And our best value for X2 is 1.5, which is the exact same optimum that we saw in the previous examples. Okay. All right. Any questions on pattern search here? Okay. All right. So that's pattern search, and so that example is available to you online. So remember, pattern search is basically the same as coordinate search. We just add this extra step here of stepping in the pattern direction. Okay. I think probably the thing that's most different about this implementation compared to example 3 is that we're using a different method for determining the step. Okay, so make sure you kind of, it looks a little intimidating, but just just kind of make sure that you kind of understand kind of this section of right, because that section is basically repeated twice, in the same. Okay. All right, so let me go ahead and bring back the iPad here. Okay. So we've gone over 4 algorithms so far in our multi-dimensional unit. So we've gone over Monte Carlo, we've gone over random walk, coordinate search, and pattern search. Okay. All these are good algorithms, and so none of these are bad by any means. But they all have kind of limitations. Okay. The method that we're going to go over, the last one, that I think we'll definitely spend the rest of today talking about it. We'll probably spend all of Thursday talking about it. This one still has its issues, and so there's no algorithm that's absolutely perfect. But this method was kind of designed to be kind of the most flexible and to have the least amount of problems compared to the other ones. Okay, this algorithm is so good that if you use MATLAB or if you use Python to just say optimize this objective function, this is most likely the algorithm that's going to be cheap. This is very much a modern method that's still kind of being used today for most problems. And so that method is called Nelder-Mead optimization. So let me start by saying that, like I mentioned, all of the other methods that we've gone over so far kind of have issues. Okay. So let me list out all of them, just to kind of refresh your memory, and then kind of talk about some of the issues that they have. Okay. So the first one we went over was Monte Carlo. Remember, Monte Carlo was the method where we just randomly sample each design variable and we just test it at all these random locations. Okay. That was probably the most unique algorithm, kind of thinking about it that way. Okay. The issue with Monte Carlo is that it has slow convergence. unless you get really lucky with the random number generator, you have to kind of repeat Monte Carlo, hundreds of thousands, millions of times, before you kind of get lucky and kind of hit the optimal. Okay. And so Monte Carlo is kind of famous for being very slow converging, but it will converge and it will never get stuck. Okay. Second one we went over was random walk. So the issue with random walk, ideally random walk is that if you start from a pretty good location, it'll converge on the optimum very quickly. Okay. So it has better convergence properties than Monte Carlo, granted that you start from a good place. But if you don't start from a good place, then random walk can get stuck in a local minima. Not only does it get stuck, but it doesn't really have a way to kind of get out of that local minima. You can do some clever things like you can restart the random walk, you can reset the step length if you detect you're getting stuck, but by itself, random walk doesn't have any mechanism for getting unstuck from a place. Actually, the next two I'm going to lump together because they have kind of. So pattern search and coordinate search are kind of, almost two sides of the same coin. One side of the coin is better polished than the other, I guess. So pattern search is a little better than coordinate search, but they kind of have the same issue. Okay. So coordinate search and pattern search it's a stepping method, just like random walk. And so it's once again susceptible to getting stuck in a local minimum. It's not as susceptible to random walk because at least you're stepping in predefined directions. And so the way most objective functions are is that if you're stepping in just one variable at a time, then you could break out. Okay. Because likely one of those directions, one of the design variable directions will lead to some improvement. Okay. But it still can get stuck. And coordinate search and pattern search kind of have also the weakness of actually not having any kind of randomness at all too. So if done correctly, coordinate search and pattern search, it does converge faster than random walk. But if it gets stuck, if it gets stuck in an algorithm, it's basically always going to get stuck. Okay. Random walk, at least you have the possibility of breaking out of a stuck location, but sometimes that possibility is very, very small. Okay. So Nelder-Mead is kind of been designed to address all these things. So Nelder-Mead, it's a fast converging algorithm, right? So the way it's designed is that it should approach your optimum fairly quickly. And there's actually built-in kind of methods or built-in kind of mechanisms within the algorithm itself to help get it unstuck. Okay. It's still possible for Nelder-Mead to get stuck. And so, getting stuck is actually a big issue in optimization. But Nelder-Mead, at least has ways to kind of break out of that slump. And in fact, it even has ways to detect if it's getting stuck. Okay. So that sounds great, right? So having an algorithm that has these mechanisms is good. The downside to Nelder-Mead, compared to the other ones is Nelder-Mead is probably the most complicated to implement. It's definitely gonna be the longest example code that we have, right? And even just understanding what the algorithm is aiming to do, I think is a little bit more difficult here. And that's kind of why I saved it for last. Okay, so how does it work? So Nelder-Mead works on this concept called a simplex. And so what we say is that, Nelder-Mead is maintaining, well, first we have to generate it, but once after we generate it, we then maintain a simplex within that design space, okay? And Nelder-Mead just ends up just kind of moving this kind of simplex around and doing kind of smart operations to move it closer to the object. Now, what is a simplex? A simplex is basically a polygon in n-dimensional space. So a polygon is simply just a shape, and so we're gonna be doing a lot of geometry, for the rest of today and for Thursday, okay? But it's a very special polygon that, the number of vertices or the number of corners that it has is n plus 1. So if you have a fixed kind of dimension, so that means your simplex is going to be a fixed shape as well. Okay. So for instance, in 2D, and so in 2D, that's two-dimensional space. Your simplex is a triangle because a triangle is a connection of three distinct points. One, point two, point three. Okay. Three D. 3D is three-dimensional space. So that means our simplex will have n plus 1 points, which is 4. Okay. So a shape with 4 vertices and 3 dimensions of space, where each vertex is connected to the other, is what's known as a tetrahedron. If you've never seen a tetrahedron before, a tetrahedron is basically a triangle, or excuse me, a pyramid with a triangular base. If you're into Dungeons and Dragons, that's your D4 basically. Right, and of course, this idea of a simplex kind of abstracts to 4-dimensional space, 5-dimensional space when you have 4D, 5D optimization problems, but it gets much more difficult to draw in 4D space, if not impossible. Okay. Okay. So the way to interpret Nelder-Mead is that each point on the simplex, each of the vertices basically represents a different design point in the design space. And so if each of those points are a unique design point, that means each of them also have a unique evaluation of the objective function at that point as well. That means alongside each point right here, we have an F1, F2, F3, okay, F1, F2, F3. All right. So the idea with Nelder-Mead, so keeping this in mind that we have a simplex that we're maintaining with a set of distinct points, okay? The idea with the Nelder-Mead optimization method is to use the simplex, right? So use our design points around the simplex and use each of the function evaluations around the simplex and manipulate the shape and location of the simplex so that we gradually move it closer to the optimal point. Okay. So it's actually kind of a really interesting algorithm to kind of visualize in practice. And actually, if you search up on YouTube, Nelder-Mead, simplex optimization, you actually get to see the simplex kind of move to a location. Now, I can't do fancy animations because it's just me and an iPad here. But there's a lot of really cool animation that you can look up on YouTube. Okay, but basically the idea is this, right? And so if we have kind of two-dimensional space. So here's our typical design space here. So we have X1, X2, right? And let's just say for the sake of argument, we know where the optimum is. So with Nelder-Mead, so in two-dimensional space, we know that we're working with a triangle. The idea is to move this entire triangle over towards the optimum by basically, generating new points and swapping out some points in the simplex. Okay. So for example, one of the operations that we'll go over that we'll talk about in more detail on Thursday is called reflection. So reflection is kind of the main operation that we're going to use the most. Okay. So the way reflection works is that, at each point in your simplex here, you're going to have values for each of the objective functions, or you're going to have an evaluation of the objective function at each of those points. Okay. One of those points is going to be the worst one, right? And so the way reflection works is that we're going to basically kick out the worst one. Okay. And so for instance, let's say that point 1 here has the worst value of the objective. Say that F1 is worse than F2 and F3. Okay. So we kick that one off the simplex, we wrote him off the island basically. Okay. And then we generate a new point, Okay, so let's say we generate a new point here. Or and then now our simplex, now that we've picked out point 1, okay, our new simplex is going to be generated from points 2, 3, and 4. F4. And so by kicking out one point and generating a new point, that you know, if you kind of look here, F.4 is kind of opposite of where point 1 was. We've moved the simplex closer to the op. Now we can do the exact same thing. Okay, so let's say that in our next step of the algorithm, we see that F3, we say that F3 is worse than F2 and F4. So F3 is worse. Let's kick him out of the simplex. Let's generate a new point. Okay. We'll generate a new point that's kind of opposite of where point 3 was. So we'll call this point 5. Make a new simplex. You make a new function evaluation here, F5. Okay. Once again, the simplex moves closer to the op. Right, so you can see here that, you know, one point at a time, you know, we move kind of closer to the optimum. And even for the points that kind of maintain the same, right? So you can see here, point 2 has kind of stayed the same in all 3 cases, right? We use the different points of the simplex to perform comparisons as to where we should move next. Okay. And so using a simplex like this actually solves kind of 2 kind of main issues that we had with, you know, in particular coordinate search and pattern search. And that not only is our step direction determined by the simplex, but our step length is also determined as well. Okay.
So since it's so since this is a 2-dimensional environment and we're using Nelder-Mead, that means unlike the previous examples, we're now going to be starting out with 3 points.
Exactly. Yeah.
So now we do 3 points, each with their own individual steps.
Yep. Well, there's a way that you can generate the initial 3 points. Usually you're just going to take like an equilateral triangle around the group. And so one thing that you'll see is that, you know, we'll probably pick a center point, which is probably be 0, 0, and we'll pick 3 points that are just equidistant from that one, and that'll be your starting simplex. There's a way for us to generate that initial simplex. You usually generate the initial simplex is not that big a deal, but you know, there's different ways. In fact, let me kind of so we'll go over the exact formula for next time, but let me kind of show you how the initial simplex is. Okay. So the way initial simplex is usually made is you have some kind of center point. This right here is a center point. So the center point is kind of similar to, you know, if you think back to coordinate search and pattern search, that's kind of our starting point. So that's kind of the idea here. Okay. And the idea is to generate the simplex around the center point. Okay. So for example, in 2-dimensional space, you know, maybe we make, you know, maybe we add a fixed amount, x2, right? That's going to be one point of our simplex here. Maybe we add, we subtract a fixed amount in x1. That's gonna be point number 2, okay? And then maybe we move in a pattern direction, so, you know, let's say that we choose kind of a fixed amount in x1 and x2. Let's say that we make another point x3 here. This direction, this amount is L, this amount is L, right? This amount might be L as well, right? So these are all kind of predetermined. And if you connect all 3 of these points, that's going to be your initial simplex so that you can kind of start the algorithm. So this point 1 right here might be, you know, x1, well, I think that'll just be really good. So we'll go over the exact formula for this. We'll start with this on Thursday. And then once you kind of have that initial simplex, then you can kind of start rolling with, you know, the different operations. All right, any questions on this before we wrap it up for today? Okay, all right, so we'll pick this up next time. So we'll go over, so we'll start with the initial simplex and we'll get into reflection and contraction and shifting. And then we'll do an example, we'll kind of take our time with that. And by the time we finish the class on Thursday, then we'll have finished this kind of our dance unit that we have multi-dimensional nonlinear program. All right, so thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you guys on Thursday.
Professor,
What's that?
have you posted the solutions for the last homework?
Not yet.
Okay.
I need to kind of format it and look at it, but yeah, I'm planning to do that probably tomorrow or Thursday.
Perfect. Thank you.
Does the study guide doesn't go out as well, or is there already out?
It's already out. So I sent an email to everyone with the study guide.
Okay, that
You
was
should be able to see it's if you look on the week 12 page, it should be.
okay.